Welcome everybody. It's time to continue with our meeting here, and it's a rather special session. We are using this opportunity of the meeting at Niels Bohr International Academy to finally settle a wager that has been long underway. A little bit of the history is listed here. It started out in 2000 when we held a meeting on the premises of Leidensweg, and there are many people here in the audience who signed the original wager in 2000. The story is that we should meet again 10 years later to check whether supersymmetry had been found or not at the Large Hadron Collider at CERN. For various reasons we got delayed, and we actually met in 2011. That means we gave let's say, the yes side one extra chance. And even then, in 2011, it was decided it would be an unfair way to settle the bet, because the Large Hadron Collider at CERN had been delayed for a number of years for various reasons. So we were generous, us who voted no then, actually, and extended the bet for another 6 years or 5 years. But now the official date would be by 16th of June. We could not hold the meeting at that time, but we are settling it today. You will see that there are a number of names you may recognize on this list, both on yes and no side. The first person to sign the list, the wager here, was Gerard Toft, who in fact also had a footnote where he says that both sides will claim victory. Now, Gerard Toft was supposed to be here, but unfortunately was not able to make it. But he has kindly prepared a file for us, so we'll just run that file for you now, and then you can hear. I believe he will also tell a little bit about the story, the history of it, and why he voted the way he did. So.
In June 21 of the year 2000, a group of physicists were together in a meeting in Copenhagen dedicated to non-perturbative methods in field and string theory. They agreed upon having a wager on supersymmetry. Will a supersymmetric partner of any of the known particles be experimentally discovered within 10 years' time? There were really two issues here. One, we knew that there really was only one facility in the world where such a discovery could possibly be made: the Large Hadron Collider. We were asked to bet whether or not this machine would collect and analyze enough good statistical data within 10 years' time that would enable physicists to confirm the presence or absence of the particles that we were thinking about. And two, we were asked to bet whether or not supersymmetric particles with sufficiently low masses would actually exist, and whether they are awaiting discovery like sitting ducks. I was not really interested in participating in the first part of the bet. And indeed, it did happen. There were considerable delays in the commissioning of the accelerator. More than 6 years extra were needed, partly due to the usual types of delays, the ones that occur only too often in such large multi-billion euro projects. But partially also due to an unfortunate setback when an explosion took place near one of the 1232 main dipole magnets, which slowed the machine down by another 2 years. This is why I was in favor of a postponement of the waiver by enough years, so that really only the second part of the bet would become the main decisive issue. Do such particles exist? Do such particles exist? Does supersymmetry exist? Supersymmetry would be a property of space, time, and matter. The evidence for such a symmetry is circumstantial at best. It could be an approximate symmetry, but even for that, no direct signs have ever been found. Supersymmetry would be an essential element in string theory. But string theory also does not have solid support in experimental evidence, be it direct or indirect. It is an unsatisfactory element in these theories that supersymmetry must be broken, and the origin of the breaking mechanism is not so clear. To summarize the problem, why does string theory generate such a very special symmetry? And why is it not an exact symmetry after all? Supersymmetry has not, or not yet, fulfilled its promises. It does not really enhance our understanding of the universe. And it is my intuition not to trust such a theory with so many loose ends. And therefore I find it difficult to support the theory of supersymmetry strongly. To me, supersymmetry looks too much like a religion, with its missionaries and its deserters. This is why I added a footnote when I stated my side of the bet. Even the most dubious signals will be grabbed by the loyals as evidence. My present position towards supersymmetry is that supersymmetry is an elementary and important mathematical property of quantum field theories, including gravity. But it doesn't have to exist as a conspicuous symmetry in nature at all. In addition of my being skeptic against the expectation that supersymmetry will one day be an elementary ingredient of particle theories, I would find it even more unlikely that the mass values would be just small enough to allow detection of such a symmetry in the next rounds of experiments. That really sounds a bit too much like wishful thinking. I do know the arguments, I just think they are far too optimistic. However, let me end with a positive note. You see, supersymmetry refers to the spin of particles, a property involving rotations in space. If proven true, contrary to my expectations, supersymmetry will be the first major modification of our views of space and time, since Einstein's theory of general relativity in 1915. Minkowski space then becomes superspace. Therefore, whatever the outcome of this waiver, or future waivers on supersymmetry, these outcomes will be of extreme interest for fundamental particle theories. In June 21 of the year 2000, a group of physicists were together in a meeting in Copenhagen dedicated to non-perturbative methods in field and string theory.
It was actually a closed time loop. I should add also that Stephen Hawking, who is with us today, was not present in the meeting in year 2000 and was not present in the meeting in 2010/11 either. But we could get a statement from Stephen today, perhaps.
I was last here in Copenhagen in 1970 at a conference on general relativity. There was a furious argument because the previous conference had been in Soviet Georgia in 1968. Many people boycotted because of the Soviet invasion of Czechoslovakia, or because no one from Israel was invited. I am pleased to be here in Copenhagen again, and interested to hear the outcome of the wager. I believe if there was supersymmetry, super partners should have been observed. If I had signed up to the bet, I would have voted no.
Okay, that was a clear statement, and now it's time to decide actually who won. And Nima Akani Ahmed from the Institute of Advanced Study in Princeton has been kind enough to literally fly in this morning to settle the bet and give also the arguments for why he decided the way he did. You need the pointer?
No, I'll in a moment. But first, let me say, I really have no idea how I became the adjudicator of this.
Sorry.
Trust in this.
Sound on here.
Oh, do I need sound? Sorry.
Ah.
I was not.
Device. Hey, you have to stop.
Wait, Lindsay, you'll be wired. As if
Very good. As I said, I really don't know how I ended up as an adjudicator of this for a couple of reasons. I signed in the second round. I have typically not ever gotten involved in bets like this. There's all kinds of bets. Theoretical physicists like to take bets on all kinds of things, and I've always taken a moral high ground on this, on betting about things in physics. That things we don't bet on these things. Nature decides. You know, it's all we're all in the pursuit of truth. We're all on the same side. But we're at a very nice restaurant here, and this piece of paper went by, and so I thought, this time, you know, why not? And I was thinking why it is that I should be made to suffer in this particular way. And it occurred to me that it's really a payback for the sins of my youth. Unlike maybe many people who end up with academic careers, I was not a good student in school. And one of my big problems was not getting homework done on time. So it was a constant battle with my with my teachers that asked if I did my homework, and I'd say, no, but just give me another week. Just give me another week. It's kind of like the bet, okay? Give us another 1, 2, 3, 4, 5 years in order finally to settle things up. But well, back then, because the teachers were always anxious to get rid of me, I'd get my C or D and get moved on to the next year. Here things are a little bit more serious, so we do have to pay up eventually. Okay, so I think it was really very gracious of the people who made the bet the first time around to actually extend it after 2011. They could have legalistically claimed victory then, and 5 years was very generous a wait. If one believed in a very conventional picture of what's going on. By the way, Professor at Tufts didn't explain it, but one of the major motivations for expecting supersymmetry to lie around at accessible energy scales goes back to arguments that he himself gave us in the 1970s. Really, those basic principles or those basic expectations, more so than the specific framework of supersymmetry itself, which is a very concrete instantiation of those examples, which is being put under great pressure from the LHC. Anyway, so it was more than fair to give it another 5 years, and I think if one believed in a conventional supersymmetric picture of the world, this was a very good time for things to show up. This is really the 11th hour for things to show up. We should remember the LHC has collected roughly 1% of all the data that it's ever going to collect in its lifetime, so we do have quite a ways to go. And the reach for the masses of particles is going to go up by a modest factor, maybe almost a factor of 1.5 or 2 compared to where we've gone so far. Nonetheless, if you believed in that picture of the world that a lot of people believed in, especially fervently around the year 2000, then it was very fair to sign on the bet, very fair for this particular time scale. And so with that, let's first settle the bet aspect. Now, here is one bottle of cognac. Okay. Now, can we put the thing back up? is it possible to put the bet back up? Because there's something very, very important here. Actually, first, does one of the winners want to come and accept it on the behalf of the winners?
On behalf of all the winners.
All right, but why don't you accept it for the moment? But then we have something important we have to talk about.
Back.
No, I'm not taking it back. Oh, sorry. Notice that it had to be more expensive than $100. Notice, okay? So actually, this was procured by Jacob Burgeli, who's here at the NBI, right there. I asked Jake to go buy the most expensive bottle of cognac he possibly could, and that I'd pay him back. Remember my story about the teachers, okay? Make sure to ask me for the money, so otherwise I might never see it. Anyway, so this costs definitely more than $100. How much did it cost exactly, Jake?
1,000 crowns.
Okay, very good.
You don't want to get rid of it.
No, go ahead. Okay. It's all yours. However, we settled the bet. Well, hold on. But there is something we have to decide. Because something which has been brought up by a number of times is it's not clear whether the winners are owed, 25 bottles of cognac or 1. So I thought we would take a vote from the members of the audience, actually reading the bet. See, because it says by signing yes or no, you promise to deliver a bottle. Now, what's not completely obvious is whether the you is a collective royal you or a highly individual, biting, brutal you. Okay. So why don't we decide, huh?
By signing you is an individual act. When everybody signs,
Yes.
sign individually. So it means everybody has to.
Everybody's got to pay. All right, David.
Besides which, if you look at the next paragraph, there's a proof that you as an individual.
Yes?
You is used to make a choice.
In case you are wrong. Oh, I see. Sorry. Right.
It's clear.
It's clear. All right. In that case, well, I'm good. So. All right. Now, I think we're going to move on to have a discussion, but I wanted to open things by saying a few words. Because actually, now kidding aside now, something dramatic and interesting is going on. Our 6,000 experimental friends have worked the better part of 2 decades of their lives, one way or another, to deliver some news that would be very surprising to the theoretical physicists of 1995 or 2000. Nonetheless, in my own signing of the bet was a rather unconventional one, because for quite a while I myself have not believed in the conventional supersymmetric picture of the world. And what I'd like the panel to talk about, and I'd like to just kick it off briefly, giving my own 2 cents about it, and hopefully we'll hear from everyone else, is the answer to the question, what the heck is going on? Okay, what the heck is actually going on at the TeV scale? And my own best bet for what's going on, and I've really thought this since 2004 or 2005, is not the conventional supersymmetric picture of the world, where it really is the 11th and a half hour for things to be showing up now, but a variant of that picture that back then we called split SUSY, or the minimal version of split supersymmetry. And in this picture of the world, it was really always a 50-50 proposition whether the LHC would or wouldn't see new particles. And the reason I signed yes was just optimism, hoping that the answer would end up being yes. But it's not like the standard supersymmetric picture where you really expect to be seeing, you're deep in the heart of the parameter space where you should be seeing stuff. So I just want to spend a few minutes telling you what this picture was. And also to point out to those of you who aren't familiar with the subject, that it is not the case that things were going along fantastically and everyone in the field was totally convinced that we were going to turn on the LHC and super partners were going to come pouring out, and that it was the failure of seeing these things at the LHC that was the wake-up call. It's not like that at all. There's a fraction of theorists, maybe not the majority, but a decent-sized minority of theorists that already, since the late 1990s and early 2000s, have been saying something is wrong. It's not obvious that it was something greatly wrong, but it was at least something a little bit wrong. And the tensions actually go back even earlier than that. So it's actually a tension that's driving research in physics beyond the standard model for 30 years, right at the very beginning of this whole endeavor, we're following Ken Wilson and Gerardo Tuft. We took this principle of naturalness seriously. We had to imagine there was lots of new particles, structure at the TeV scale in order to solve the naturalness problem, and that was immediately in tension with the fact that we had failed to see indirect evidence for new particles from things like violation of baryon and lepton number, violation of flavor, and CP. Back then, in 1979, 80, 81, these were not thought of as problems, they were thought of as opportunities, that there had to be some special structure to this physics that solved the naturalness problem while avoiding these constraints. But these stories started piling up as time went on, the indirect things were not seen, and then more and more the direct signals weren't seen. Nonetheless, there was, I think, a period of peak excitement about the idea of low-energy supersymmetry. It's not true that it was just a completely collective delusion with nothing to support it at all. It's a theoretical idea. It's a beautiful symmetry. It's the most concrete solution of the naturalness problems associated with the Higgs. And then this amazing picture happened when LEP measured very precisely the gauge couplings of the strong, weak, and electromagnetic forces around 1990, and we saw that with supersymmetry at the TeV scale, these couplings converged to a point to percent level accuracy. And somewhat more qualitatively, we had the picture of weakly interacting dark matter. These were both things that didn't have to happen, that just fell in your lap once you imagined that you had supersymmetry at the TeV scale. Nonetheless, even then, even from the LEP era, between LEP 1 and LEP 2, by the end of the 1990s, there was some beginning of a feeling of unease about low-energy supersymmetry. And the reason has to do with something sort of qualitative, that the typical supersymmetric spectrum that people expected. Remember, this is supposed to be a theory of W and Z masses. W and Z masses are not 1,000 GeV. They're 80 and 90 GeV. So you would expect in such a theory that the superpartners would show up around the W and Z scale. And actually, a little bit more in detail, in supersymmetric theories, typically the colored particles are heavier than the uncolored ones. And so, on the other hand, the Higgs is dragged to where the colored guys are, in particular where the stops are because of the large top Yukawa coupling. So the typical spectrum you would have expected would have had the Z and the Higgs near the top of the spectrum, along with the stops and the gluinos, and then maybe the sleptons and the electroweakinos underneath them. People would have been thrilled with 50 GeV sleptons. That would have been great, would have been perfectly fine. 200 GeV squarks. That's what supersymmetry should have looked like. And not crazy people, not the same people I won't name who have been saying for 20 years we'll discover supersymmetry in 6 months, but much more sober, reasonable people really strongly believed that LEP would discover supersymmetry. When LEP, especially LEP 2, failed to discover supersymmetry, that was the beginning of a qualitative problem. Okay? Again, not clear if it's a huge problem or a small problem, but it was the first crack in this narrative that was working otherwise very well up to that point. Okay. So again, it is not then the case that it was the LHC that bonked everyone over the head. Okay? If you were paying attention to the data and you were sensitive to the data, you were already worrying in 2000. In fact, let me say something right now. People in the year 2000, I remember very well, would go around giving talks about supersymmetric models, and the spectra in these supersymmetric models would have stops at a TeV and gluinos at a TeV or 2 TeV. And Higgsinos at a TeV, and I would complain to them. I would say, this theory is very unnatural. What are you talking about? And they'd say, oh, come on, who cares? This is nothing compared to the Planck-weak hierarchy, and they just brush it aside. They were forced into those parameter ranges to get the Higgs mass heavy enough, for example. That's one of the facts about supersymmetric theories, that the Higgs mass wants to be close to the Z mass. So I think those people were underreacting in 2000, and they're overreacting now. What we've learned from the LHC up to this point is essentially confirming directly that picture that we're already suspecting indirectly from around the year 2000. It's just that various loopholes for what could be happening were closed. Okay, now, all these niggling things wrong. We don't see evidence for flavor change neutral currents, electric dipole moments, all these other things. Of course, there was a humongous problem, elephant in the room, we all knew. There was this crushing weight on the notion of naturalness coming from the cosmological constant, which is very, very unnatural by any standard picture. There's no new physics at the millimeter scale, which would naively be the natural scale associated with the cosmological constant. And that was only exacerbated after we discovered there was an accelerating universe, so we couldn't imagine some magic mystery mechanism that would make the cosmological constant exactly 0. And so that began some people taking seriously the idea that maybe some things will really be finely tuned, and whether you may or may not want to use the A word, the anthropic word, to explain things like the smallness of the vacuum energy. But in any case, that was an elephant in the room that was there all along, and but people's attitude was that, well, if something like that is true, maybe it could be also be true for the hierarchy problem. Some analog of these reasons for tuning for the weak scale could also be true for the hierarchy problem. But why should we take that seriously? Because we have this great evidence that supersymmetry is on the right track. We have gauge coupling unification. We have dark matter. All this stuff works. Why would it look like it was working if in fact everything was attuned? That was the tension. There were two things pointing in opposite directions. Unification in dark matter, as things are on the right track, and naturalness, of course, and all these other niggling problems on the cosmological constant as a big thing that's staying on the wrong track. That was certainly my psychology, and the reason I didn't take, I continued to think through to 2003, 2004, that indeed something like low energy supersymmetry was on the right track despite these niggling issues with it. It was this picture of minimal split supersymmetry that changed the psychology for me radically. This is a picture where supersymmetry is broken in really in the simplest possible way. But in the absolute simplest possible way, the scalars and the fermions don't want to be naturally degenerate with each other. And the reason is that you have to break more symmetries. You have to break an R symmetry to keep the fermions light. So it's natural to have a loop factor difference between the scalars and the fermions, which would mean the scalars could be at hundreds of TeV, and the fermions could be at the TeV scale. In this picture, we get rid of all the indirect difficulties. But I just want to finish a quick train of logic associated with this. So in other words, it's possible to have a theory that's supersymmetric, with supersymmetry broken in really the simplest possible way. It's incredibly finely tuned from a conventional point of view. That's the heresy about this idea. I remember giving talks about this in 2004, 2005, and literally people I respect a lot were yelling at me, not for questioning that naturalness might be wrong. We certainly were saying that naturalness was going to be wrong at the TeV scale, but because we dared to say that supersymmetry would be unnatural. And that was crazy, because the thing that's supposed to solve the naturalness problems was going to be unnatural. Of course, it was very unnatural for the cosmological constant the whole time. Okay, so that is the picture, and it has one prediction. It predicts the Higgs mass. It predicts that the Higgs mass should be between 120 GeV and 135 GeV. And the fact that it's at around 125 GeV is perfectly decently compatible with this. All right, so that is a picture of the world. Various things work out nicely. But what I want to say is that in this picture, it was not guaranteed that the particles should be accessible to the LHC. The motivation for having these supersymmetric particles around is dark matter, and there's different pictures for what dark matter could be, just qualitatively different pictures for what it could be. Some of them where the particles are accessible to the LHC, some of them where they're not accessible to the LHC. And back in 2006, we had talked about this very explicitly for the two different sets of possibilities, and again, having the bottom of the spectrum where the dark matter particles are at 1 or 2.5 TeV was perfectly fine. It would make split SUSY invisible at the LHC, but there was other possibilities where it would be visible, and we just don't know ahead of time, because by abandoning the naturalness criterion, we're not forced to have these things accessible to the LHC. The reason I signed the bet was optimism that we'd end up in the 50% of the parameter space where it was visible at the LHC. And it's possible that the next 99% of data that we'll gather from the LHC, if we're lucky, some version of this picture might be right. So let me just end by saying, apart from these discussions about what we think is going on, and I hope the rest of the panelists will tell us what they think is going on, nonetheless, I think it's definitely fair to say, and it's true, that what our 6,000 experimental friends have done is give us a very, very big clue from nature. It was not a clue that many people expected 20 years ago, and we have to take it seriously and think about it hard. I think it's important to go back to the drawing board and think again about entirely new solutions to the cosmological constant and hierarchy problems. Some sort of crazy, weird, not great ideas have started coming out in the past year or two for the hierarchy problem, relating them to cosmological dynamics in various ways. These ideas look kind of crappy right now, but it could be we're in the local basin of attraction of a wrong set of ideas, and we have to get out of them to find the right one, so we might have to tolerate a little bit of crap for a while in order to get there. So with that, I will close.
It was great to hear Nima Kani-Ahmed with his extremely optimistic version of the losing side. They already started discussing, but you should be wired up first, and so we can all hear what you're saying. But I want to present the panel first. We have David Shee, we have Jonit Hochberg, Nima you already heard, and we have David Gross sitting here. Now, those of you who know these four people will know that they have all four certainly expressed very positive sentiments about supersymmetry and finding it at the LHC. Two of them signed, David Shee and Nima Kani-Ahmed signed actually that it would be found. Jonit Hochberg, maybe we should consider like an agnostic, but has certainly worked on supersymmetry phenomenology and the implications at the Large Hadron Collider. And David Gross, who I understand has his own bet, which I'm afraid he will have to settle quite soon. And it is interesting because David is usually right about these things. So
being right about this one hasn't been.
So I look forward to hearing what David will have to say. But let me begin by first saying that we heard Nima was explaining that it's only 1% of the data coming in. There's certainly room for more. On the other hand, I would like to hear the panel's view that, after all, this is a silly date to settle such an issue. Have you found supersymmetry or not? It's a random date that was picked, and but nevertheless, I think there is a sentiment among many physicists that perhaps if this is a kind of milestone, that actually we have reached some sort of milestone where actually the mood may change a little bit among physicists about the relevance of supersymmetry at the energies of the relevant for the Large Hadron Collider. But I leave that up to you. As I explained, I'm the only one on the winning side, and we have. I think Winston Churchill said that in victory you should be magnanimous. I know also he said that in defeat you should be defiant, and that's certainly Nima. So we look forward to hearing your views now, because you're on the losing side, but we want to hear your views.
Are we on the losing side?
But I think Nima, I think we first
No,
started.
I'm not on the losing side, but I would have been. And there's a very good chance I will be for a much more expensive bet.
Oh, really?
No, it's not this. But no, I wanted well, before addressing that question, whether this is a milestone or not, just address some of the issues that Nima brought up. So he explained why supersymmetry is attractive. Those reasons haven't gone away, not only because they continue to be outstanding features of what we don't understand about the universe, how unification takes place, what is the origin of dark matter, and potentially explaining electroweak hierarchy, and a few other reasons as well. But because people haven't come up with alternatives yet. I mean, there better be, if supersymmetry doesn't work, other explanations, but it's not as if people haven't been thinking of them for the last 40 years. What the discussion has, and to some extent continues to be, is over something called naturalness, which Nima didn't explain, or Gerard, who was one of the inventors of the strategy. I regard naturalness not as a law of physics, a principle of naturalness, a concept of naturalness, but simply a strategy. It's a strategy which we teach undergraduates. If you want to understand a physical situation, take the relevant scales, physical scales involved in the problem of dimensionless constants that come into our framework, theoretical framework for understanding the physical phenomena, and you can easily, or if you don't, we'll teach you how to come up with a back-of-the-envelope estimate as to the order of magnitude of the relevant physical quantity we're discussing. So that, to some extent, that's what naturalness is. There's more that goes into it. It relies on decoupling of scales, on locality in a way, sort of basic concepts of the way we look at the universe. But it's a strategy. The dimensionless numbers you come up with this input should be of order 1. And if you have to adjust them to 1 part in 100, well, that smells a bit. Who ordered that? Why is it not of order 1? If you have to adjust it to 1 part in 1,000,000, that's really suspicious. If you have to adjust it to 1 part in 10 to the 20, that's truly suspicious. You obviously have failed miserably by a back-of-the-envelope calculation. Something else is needed, some other principle, some other small number that comes from some dynamical effect. So it's a good strategy. It's a strategy we use all the time in physics. It's been a little dressed up, in my opinion, to become a principle, so that when Nima would get up and talk about split supersymmetry, which he just told me involves adjusting parameters to maybe 1 part in 100 or 1 part in 1,000, that is unallowed. Now, of course, if we look at the real world that we measure and observe, and we fit it by the standard theory, which works with exquisite precision, there are many small parameters in that model, which we've measured with exquisite precision, and we have absolutely no understanding of them. And they're much smaller than 1/100th or 1,000th, using masses, not mass squared. So the mass of the top quark divided by the mass of the bottom quark is roughly 53,000. Very unnatural number. The natural standard model would have all the quark masses the same, all the lepton masses the same, all the couplings the same, or at least at some energy, which they actually do. The couplings differ by factors. Well, it's a running difference, but at the energies at which they were first measured, or typical scales of the strong and weak interactions, they differ by factors of 10 to 100. Doesn't bother us, partly because we understand how they unify even better with supersymmetry, but even without it at the Planck scale, and no big deal. We understand the dynamics that produces that small number, and it's not so small. Now, there are many of these small numbers, truly small numbers, that dictate the form of the universe as we know it. And Nima referred to some of them, the cosmological constant and the electroweak hierarchy. The third is actually the one that Dirac first pointed attention to, which is why is gravity so weak? Or why is the mass of the proton 10 to the minus 20 times smaller than the Planck mass? This bothered Dirac, and he couldn't explain it. We now have calculated that, or QCD has calculated that. We understand that masses vary linearly with energy and couplings logarithmically, and the log of 10 to the 20 is a number we can understand and indeed calculate. So small numbers, even of the order of 10 to the 20, are calculable if you understand the dynamics. In the case of the hierarchy, supersymmetry offered the opportunity to explain the same quantity, same kind of big number in terms of by turning it into logarithmic effects, and still remains the best hope for doing that. There might be others, indeed. The cosmological constant, which is a totally different kind of issue, is similar scale when you convert it to masses, and we have absolutely no idea for that. Those are serious conceptual problems, and their resolution, for example, in the case of the proton or compared to the Planck mass, or why is gravity weak? Why don't we form immediately black holes? That we can explain. That required truly new understanding of quantum field theory, which wasn't available to Dirac when he posed the problem in the 1930s. We have no similar explanation of the cosmological constant. So to relate such different kinds of lessons to be drawn from the existence of very small numbers, which in some cases we've learned how to explain, in other cases we have absolutely no idea, to each other seems to me wrong. Each is its own sign that we're missing something fundamental. The reason I still believe in supersymmetry largely is because that's the only dynamical explanation we've come up with for one such large number. But those are numbers of order 10 to the 20. When you get down numbers of order 10 to the 2 or 3, it doesn't bother me. I mean, in the history of the Standard Model, nobody, if somebody was told back in 1960, there's going to be a third generation of leptons and of quark and of whatever you want to call them, strangeness, you know, top, bottom, and those quark masses are going to be 50,000 times heavier than the quarks that make up the proton. People would have said, that's absurd, that's crazy, that's totally unnatural. We measure them, we have no theory of them, we accept those numbers. They are also exactly like the unknowns in the supersymmetric extension of the Standard Model, buried in the couplings to the Higgs, which we have no understanding for in any fundamental way. So I regard, you know, supersymmetry doesn't show up at the LHC or only very tentatively. That's just a sign that there probably are small numbers involved, just like there were in the quark and lepton mass spectrum. So what? On the other hand, in the absence of any positive experimental evidence for supersymmetry, we should indeed, I mean, it's always good. This is a good time to scare the hell out of all the young people in the audience and tell them, don't follow your elders, you know, these are great ideas. You know, there's some indication that they might not be sufficient. Go out, look for something new and crazy and powerful and different especially. That's definitely a good lesson, but I'm too old for that.
Nima, you had your chance. We have really a tight program, so I think we pass it on to Joni Hochberg. But stay, we could still have a chance. Yeah.
So I was, when I was a first-year graduate student, there was a very prominent leading figure in the field of supersymmetry who came to give a colloquium at my home institute, and the whole colloquium was about this beautiful framework of supersymmetry, and what he said at the end really resonated with me, and I think really influenced the way that I view this, which was that even though his field of research was in supersymmetry, he said that, you know, the LHC will turn on and who knows what we're going to see. Nature's probably going to be even smarter, even more beautiful than what we have come up with. And so my take from that was supersymmetry was this amazing playground for us to develop tools for searching, for us to understand quantum field theory better. But I was never emotionally attached to, will we find supersymmetry or something else at the LHC? And so I think that, you know, obviously what's important to me is that we learn about nature, and I've always been really attached to data. So when the data keeps on coming out, and what we're learning from the data is that if it is supersymmetry, it's not necessarily the way that we had thought that it would look like. Maybe we're learning that it's not supersymmetry. Maybe we're learning that it's something totally different. And I think the most important thing moving forward, and this is something that a lot of people in the phenomenology and experimental community have been involved in over the last few years, is making sure that we are really thinking about new signatures that maybe we didn't originally think were going to be the most important ones. Sometimes those are signatures that will exist from some new crazy theory that you'll come up with, or sometimes it's from some non-standard version of a supersymmetric theory. Sometimes it might be a really cool signature that you could search for, even if you don't yet know of the theory that would populate that region of parameter space. But it's really important that we sort of cast our net very broadly in making sure that when we're looking at the data, we're really learning as much as we can about what's out there.
You had a suggestion also, you told me just before the...
Oh yeah, so I actually wanted to do just kind of a sociological experiment, and this is obviously non-committing, nobody's writing their name down. I was just curious if we were to...
Reporters, that's all.
just kind of to pull the room to see the partition, if you were to kind of your gut feeling, will we discover any new physics at the LHC over the next 20 years? Raise your hand if you think the answer is yes.
Are we voting?
Okay, yeah, let's do that. Okay, and then the second part of the question is, how many of you would have voted differently 5 years ago? Interesting. Okay, thanks.
Okay, so my name is David Shi. I work primarily on supersymmetric phenomenology and how it interacts with the LHC data. So I don't have too much to add to what the others have already said. I mostly agree with all of that. Pretty much in my relatively short professional career, I've been, which has coincided with the turn on of the LHC, I've personally believed that supersymmetry is probably, like David was saying, that supersymmetry is probably the most elegant and beautiful solution to these naturalness problems as well as other problems facing the standard model. So I honestly believe that we would discover, or still will discover, something like supersymmetry at the LHC. And I think I can just add a few more thoughts to what has already been said. So Nima already mentioned that we've only collected maybe 1% of the data at the LHC. I think I can also add to that that the LHC is a hadron collider. It collides protons on protons and produces a whole lot of junk. So it's a very dirty environment, and it can be very challenging to pick out subtle signals out of a huge background of standard model events, primarily from QCD. So although maybe now we're hearing from the latest results from ICHEP, for instance, that we didn't see any new physics yet, what you're hearing about are primarily the lowest hanging fruit, the easiest things that could have been there to have seen, that basically are free of backgrounds and have huge signal to background ratios. So those things and have continued to not pan out, but there are many, many more difficult and challenging signatures that will require us to collect much more data up to, and this is in part why the LHC is planned to run for so many more years and to scale up so many more factors of 10 in data. So there's still much discovery potential left, not just for supersymmetry, but for new physics in general. And I think there's two distinct issues too regarding naturalness. Whether the LHC will discover supersymmetry or not, when you first turn on the machine at a higher energy, you use up a lot of the discovery potential because by jumping up in energy, you suddenly open up a new vista to much higher masses of the new particles. So although we have the reason ICHEP is viewed as a milestone, but I think actually even more of a milestone will be next spring, something to watch out for, will be next spring when Morion presents, the next round of data, which will be up to 5 times what they have now. That will really start to be the beginning of, that'll really be, you'll have jumped up in the mass coverage. That'll be saturate that. And then after that, it's more of a slow progress. And there's some asymptotic reach of discovery of supersymmetry that we're going to saturate slowly over time. So whether or not the LHC will discover supersymmetry is a distinct question, different question from whether, even if the LHC doesn't discover anything, whether natural supersymmetry is ruled out. And unlike Nima, I think it's too early to give up on the idea of naturalness. I agree with Nima in the sense that the conventional things, what I would call vanilla supersymmetry, has pretty much been, it cannot be fully natural anymore. It could be sort of 1 part in 100 or 1 part in 1,000, and maybe that's okay, but it cannot be fully natural anymore given what we've seen. There are many, many other flavors of supersymmetry that are not your grandmother's supersymmetry, and maybe that's all that the LHC is telling us, is that it's some flavor of supersymmetry that we haven't thought of or fully explored yet. And so it could be minimal split supersymmetry, that's one flavor, or it could be many other flavors. My own personal flavor is chocolate, but it could be many, many things. So I think, and there's still much potential left. So thanks.
Okay, so time is unfortunately up. There are deadlines, and there's also a tight program of the more serious part of the conference. But still, I want to give a chance to one last comment, if someone has one. It has to be a 20-second snippet. And I think you should go to Nima.
I'll say it very quickly. I just want to say that it's the most dramatic thing that we're learning at the LHC is something about the general concept of naturalness. The fact that we keep talking about supersymmetry as the thing that we keep throwing against the wall is just because it's the best developed version of this idea. But really, if the LHC doesn't see any new particles beyond the Higgs, it's that general theoretical thought that, as David was stressing, is not super sharply defined, but which has been correct 2 or 3 times in the past century in a dramatic way. It's that thing that our experimental colleagues will tell us is not true. It's a big deal. We have to absorb it into our thinking. Again, whatever we say now, it's not something that was expected in the mid-90s. And I'll just end by saying something, that when I was a graduate student, there was such a strong feeling that we basically knew what was going on at the TeV scale. It was some version of supersymmetry. The LHC would turn on. There would be 300 GeV gluinos, tens of millions of things being produced, and that was the great theoretical structure invented by our intellectual ancestors. And therefore, the job of my generation of theorists was sort of mop up, clean up. You'll sort out the second order details and figure out what the spectrum looks like and so on, which is very nice. It would have be a lot of work to do, but the ceiling of ambition and importance of what we had to do was fundamentally lower. That is not what has transpired, and I think I've said it before, but I really think it's true. It's an ideal time to be 25 years old in this field, because you don't have to master everything that your elders have been thinking about. They have not panned out in detail, even if some version of them ends up being approximately correct. In very, very important ways, they have not turned out to be correct. So if it's a perfect time to be 25. There are lots of things to do. One can try to think radically new thoughts about some of these old problems. That's very important. Even as I said, even if they don't look that great in the beginning. A Fitzgerald contraction didn't look that great in the beginning. When you tried to rescue the motion of things through the ether, it would have seemed like a really dumb idea to do these stupid things, saying something contracts as it moves, but it ended up being part of the right answer. Okay? That's one thing. And the other thing that Yonit and David both emphasized is it's incredibly important to think about new experiments, new experimental signatures, and also new experiments. And this is a big part of what theoretical physicists can do. Our generation of people really benefited from a group of visionaries in the 80s who planned 3 decades of amazing experiments that in collider physics, dark matter, axions, a lot of things. And it's our responsibility to plan the next, to think of the next 3 decades of new kinds of experiments, and there's all kinds of new and exciting opportunities to probe fundamental physics, from big new colliders to tabletop experiments. So there's really a lot of room to be creative on very phenomenological and very theoretical grounds, and I think from that point of view, if you're very ambitious, it's a fantastic time to be in the field.
Yeah, but to add to that, there are many other, even in a phenomenological approach, there are many other questions that have been totally neglected for the last 20 years because of the emphasis on, one of them I mentioned before. We have 19 parameters in the standard model, and we don't, there are 16 that could be presumably, are quark masses and mixings. We understand nothing about them theoretically. That problem was actually the first tackled after the standard model was completed 40 years ago. And nobody succeeded in coming up with a compelling explanation, or certainly one that predicted new phenomena that you could test. That's a totally neglected problem. The issue of the Higgs and the hierarchy became more important. Supersymmetry came along. Unification is another driving force, which was one of the big motivations 30 years ago for string theory, and a lot of work. That, again, largely in recent years has been totally neglected, and again, no old open questions, which are as unnatural and ill understood as the supersymmetric mass spectrum. All of those are also lying around and perhaps should be re-looked at. And then, of course, it is conceivable, one must admit honestly, that Shelley Glashow's nightmare of the desert is actually experimentally works out. I mean, it's a total possibility, aside from the unnaturalness of adjusting the Higgs, say to we adjust it to 1 part in a million and don't care about it, then experiment will teach us nothing over the next few hundred years. So that's again a possibility which does spur theoretical approaches to this, since there are enormous unsolved theoretical and conceptual issues that still challenge the current framework of theoretical physics.
Okay, I think we'll be really well around all the issues here, so let's give a warm hand to our panelists. And especially thanks to NEMA Academy for having flown in just for this event, basically. And also thanks to Stephen Hawking and Jared Toft, who we saw earlier.